Hello everyone. In today's lecture, I will talk about two new topics. First one, I will talk about the decision theory. After I cover some basics about decision theory, I will talk about the discriminative analysis. So discriminant analysis is a classifier, but it is different from the support vector machine. And the classifiers we will cover in the next few weeks are based on the probabilities. Yes, discriminative analysis. So first, let's talk about decision theory via the risk minimization. Okay, before we start, let's maybe give you a motivation example. Let's say we are using the height as people's height as an example to classify if a person is the gender of a person. And for this case, it's not a perfect linear separable. So let's say we get some data about people's height. Okay, and the question we ask here is we want to predict the gender of a person with a height 5 feet 55 inches. Is this person with this height a man or woman? For example, we have the distributions of the height. For example, you collect the data about people's height, and you from your data you can based on the label of the genders. Usually you can have this type of data. We have the two modes. It is known that in general the female's height is lower than the male's height, right? So for this new person, so for this case, we don't have the perfect linear separable case. So for example, for a person with height 5 feet 55 inch, it's hard to say it's a man or woman. Maybe it's more reliable to say it is a man with higher probability or it is a female with higher probability with some probability. Therefore, we not only need a classifier, but we also need a probabilistic classifier. Okay, and so we need a probabilistic classifier. Okay. So one aspect of the probabilistic data is that sometimes a point in feature space does not have just one class. So this height example exactly the case where we need the probabilistic classifier. So next I will show you another motivation example. Why do we need a classifier? So suppose in the hospital, you the doctor want to check, want to predict if a patient has cancer or not cancer. Okay. And based on this doctor's past experiences, based on all the patients he see before, there are some data. Let me summarize you below. But because the doctor is an expertise, he knows, he has more information about this cancer. Suppose around 10% of the whole population has this type of the disease, this cancer, has this type of cancer. Okay, but the rest 90% of the population doesn't have such disease, cancer. And furthermore, based on the doctor's further experience, experiences information, he get some data too. For example, based on the survey from each of the patients the doctor say before, suppose the doctor also knows the occupation of each patient. For example, if the person could be his job is a miner or a farmer or other. Okay, and based on the data he had at hand, among the person who has cancer, okay, 20% of them are minors. Okay, and 50% of the person with cancer is farmer. 50%. Okay, and the rest, the people with this cancer, job occupation, the 30% has other jobs, and among the patients without cancer, okay, without cancer, 1% of them are minor. Okay, 10% of them are farmers, and 89% of them has other jobs. So based on this, based on this whole population's information and the past patient's occupation, can this doctor predict a patient has cancer or not cancer? Okay. So this is just a fake example I just made up. In reality, I think for example, the ratio of the cancer patient will be much smaller, not 10%. I just made up this example. But can the doctor guess whether a new patient come in? If we ask his job is a farmer, can we guess he has cancer? Do you think Okay. We want to get if the new patient is a farmer. Can we guess this farmer has a cancer or not cancer? Probably you are not sure, right? But can we say this patient has cancer with higher probability, or without cancer has higher probability? Okay, actually, if you are in a hurry and don't think it carefully, you might think that 50% of the people with cancer are farmers, and only 10% of the people with no cancer are farmers. Probably you would say, and then you conclude that typically a farmer, you want to classify it as a cancer patient, right? But this intuition is very wrong, because uh, because you failed to use the information about the whole population information into you. So in other words, you failed to consider the prior probability into account. Here, the prior probability is the percent of the people in the population has cancer. So how to answer this question more correctly? So we need the conditional probability. Suppose we have two random variables, one is x and one is y. Here you can think x is a person's job, occupation. Y is a person if he has a cancer or not cancer. Okay, so the conditional probability x given y can be written as the joint probability of p x y divided by the probability of y. Okay, and the probability of x. Okay, so there is a rule called the total probability, can be written as, suppose we want to know randomly draw a person who is a farmer, can be written as the probability, conditional probability among all the cancer patient who is a farmer, and times the population of the cancer population plus conditioned on the no cancer patients, his job is a farmer, and multiply the probability he does not have cancer. Okay, so therefore, for example, what's the probability you randomly pick a person, his occupation is a farmer, it equals to y given x. So among the cancer patients, what's the probability he's a farmer? Okay, so that's 50%, right? And multiply y equals to 1. So we know there are 10% of the whole population has this type of cancer. So multiply by 0.1. Plus, similarly, among the patients without cancer, the probability he has a farmer is 10%, so 0.1. Multiply the probability in the population without cancer. Okay, so after you calculate this one, the probability you get is 0.14. So in other words, we can say based on this information, we can calculate there are about 14%. So this is called the total loss of the probability. And based on this information, we can say there are 14% of the whole population are farmers. So now we understand the conditional probability and the total probabilities. Now we come back to our original question. say for a new coming in patient, for a new patient, oh, by the way, this 50% is not the probability. This 50% is the conditional probability among the cancer patients. What's the chance he is farmer? But what we are looking for is, given a patient is a farmer, what's the chance he has a cancer? So we wanted to know the reverse way of the conditional probability. So for a new patient, if his occupation equals to farmer, okay, so based on this information only, can we guess what's the probability he has cancer, and what's his probability he doesn't have cancer? Intuitively, seems he has a higher chance to get a cancer, but that's not true. That's not true. So there is a typical wrong conclusion that you think 50% of the people with cancer are farmers, 10% of the people without cancer are farmers. So you conclude that a farmer has higher chance to get cancer, but this is a wrong conclusion. So what I mean here is there is a typical wrong conclusion. Okay. %50 of people with cancer are farmers. %10 of people without cancer are farmers. And from this, people may easily conclude that this data and this information suggests that it seems more likely, suggests it is more likely that this farmer has the cancer. More likely has cancer. But this is the wrong conclusion. Why? Why is wrong conclusion? Because it ignored the cancer population. So recall that there is one more condition that as expertise, the doctor knows that there are only 10% of the population has the cancer. So it failed to consider the prior probability that only 10% of the population has this cancer. But actually what we are looking for the conditional probability given the person's occupation is a farmer. What's the chance he has cancer? And based on the definition of conditional probability, we can calculate the joint probability x equal to a farmer and he has a cancer. Okay, divided by the probability conditional probability x equals farmer. So, and then we can rewrite the numerator as y given the equals to the cancer. Okay. Condition on x equals to farmer divided by the total probability px. Okay, and this the numerator, we know all the probability in numerator. So now we want to know what, given the person's occupation is farmer, we want to calculate this quantity. And for the probability he is a farmer, we already calculate based on the total probability. The probability is 14%. Okay, and the numerator is given by the based on the past data. That 50% of the cancer patients are farmers. Okay, multiply the probability of the cancer's population. Cancer's population, recall, we have 10% of the whole population has a cancer. So it's multiplied by 0.1. So this gives us 0.05 over 0.14. Actually, if you use calculator, it equals to about 0.36%. On the other hand, we can also calculate conditional probability x given y equals to -1 by using a similar formula. Okay, but now we conditioned on the y equals to conditioned on the patients without cancer. What's the probability? Here's a farmer. Multiply the population without the cancer, divided by the total probability he's a farmer. Okay, this equals to 0.14. The numerator will equals to 10%, right? So 10%, 0.1. Multiply by population without cancer with 90%. So this equals to 0.14. Numerator is 0.09. Okay. Actually, this two probability should always add equals to 1. Actually, without a calculation of the second one, you use the first one, subtract y equals to 1, you get a y equals to negative, probability y equals to -1. But the point here, the punchline here is, after this calculation, we see, given the person is a farmer, the chance he get cancer is lower than the chance he doesn't have cancer. So if we use this as a classifier, okay, since we have higher chance we should have higher chance to classify him does not have cancer. Okay, so this means this is actually so based on, given the person's occupation is farmer without cancer, with no cancer is 64%. 64%. So actually, this is the two probability we just calculated here is called the posterior probability. It's called posterior probability. So it's and y equals to 1 and y equals to -1. That's the before the doctor seeing the patient, he knows among the whole population we have the 10% of the people has this cancer. This is called prior probability, prior information. Okay, and this whole procedure is called is a big theorem called the Bayes theorem. And the classifier based on the Bayes theorem is called Bayes classifier. So about the Bayes classifier, we can not only classify the candidate, but we can also give the probability of incidence belongs to that class. So in the previous example, so for this example, probably we should not diagnose this patient as a cancer patient, but we are assuming that we want to maximize the chance of the correct prediction. But it's not always right assumption. If you are developing a cheap screening for test for cancer, you'd rather to have more false positive and fewer false negatives, because false negative is more serious, has more serious consequence. A false negative means here a patient with cancer, but we diagnose without cancer. Okay, so false negative means somebody misses an early diagnosis and dies of cancer that could have been treated if caught early. A false positive just means that you spend more money and for the more accurate test. So in this video, I'm going to talk about the loss function. Okay, actually the loss function, so here of z and is a bivariate function z, lz, we denote as lzy. Okay, this quantifies how bad it is if a classifier gives a wrong prediction class. So how bad it is if the classifier predicts the class is a z, but the true class is y. If the y doesn't equal to z. For example, in our previous example, how bad it is if we classify the farmer does not have cancer, but the farmer actually has cancer. That's one case, right? So here I give you one example. So the loss function lzy equals to, say, if this new patient does not have cancer. So the first case, if the prediction or classification is correct, we don't give any loss. So in this case, so which means if we predict the healthy person is no cancer and the cancer patient has cancer, so these are two correct cases. There is no cost. So the loss should always be 0 for a perfect correct prediction. But on the other hand, for the first scenario, if the patient does not have cancer, but we predict our classifier classify it as a cancer patient, actually this is called false positive. And for our cancer example, maybe false positive is not as serious as the false negative. Okay, so on the other hand, it could be that the patient has a cancer, but our test failed to detect it. So this is called the false negative. So if a patient with cancer, the truth is the patient has cancer, but our classifier classified it as no cancer. So this is called false negative. And it depends on how serious it is, how badness it is. For the true positive and the true false negative, we can assign some numerical values to it. So in this cancer diagnostic problem, I think the false negative is more serious, which means if you classify the cancer patient as a healthy patient, so this means somebody misses an early diagnosis and could die of the cancer that been treated if could have been treated if caught earlier. So in this cancer detection problem, false negative has more serious consequence than the false positive case. So here, we give a bigger value here for the false negative. Say we give 5 here. Okay. On the other hand, false positive means the person actually is a healthy person, but we fail to detect it. Is healthy person, but we give false alarm, saying he has a cancer. Okay, so in this case, we give a smaller loss. We say let's give 1. And in last video, we calculated that there are 36% of the probability of loss 5 is worse than 64% of the probability of loss 1. Okay, we get 36 and 64. And for this case, we recommend further screening. And for such loss function is called asymmetric loss function, which means the false positive and false negative, we don't assign the same value. So it's asymmetric. So for the symmetric loss function, it is the same, give the same value for the false positives and false negatives. So here I give you one example. There is one commonly used, if you do not have any preference on the false positive or false negative, we can use the 0-1 loss. If they correctly predict the label, we give 0 loss, and if it's give the wrong label, we give 1. So this 0-1 loss function is called symmetric loss function. So for the correct prediction, we give loss 0. For the wrong prediction, we give loss 1. Okay, so this is an example of the symmetric loss. So maybe I can give you another example that false positive could be more serious than the false negative. For example, the spam email classifier. So we want to use our classifier to classify if an email is a spam email or not. And for this case, maybe putting a good email in the spam folder has more consequences and more serious, more worse than putting a spam email in the inbox. Right? If you put a spam email in the inbox, you just delete it. But if you put a good email to the spam email box, you may miss some of the good important information, right? So putting a good email in the spam folder. Okay, so this is a false positive. Okay, usually this is much more worse than putting a spam email in the inbox. So this is called a false negative. Right? So if you have, so for this case, you have false negative email, you just delete it, right? You just, but if you put a good email in the spam folder, you miss important information. Okay, so in this case, maybe the false positive will give larger loss than the false negative. So that's about the loss function. And based on the loss function, we are trying to find the decision rule. Okay, so now let's say a decision rule. We call it R, is a function of the RD. RD here means the feature space. Okay, we classify for each given case with the D features, we want to classify as the positive one or negative one. Is a function that maps D features, D feature vectors. D feature vector into two class, one or negative one. So let's say for the binary classification first. In future, we're gonna give you more multiple class classifier. Okay. So given any decision function, okay, we also call this one as in the class, and the negative one is not in the class we cares about. And now we are ready to talk about the risk for each possible classifier. Okay, the risk for the classifier R is the expected loss over all values of x and the label y. So x is a vector, and the label is just a scalar 1 or negative 1. Okay, and mathematically speaking, the risk function of the classifier, a decision rule, okay, is equals to the expected value. So the risk is a function of the decision rules. So it's a function of the function. And in mathematics, we call it functional. It equals to the expected value of the loss And this expectation is over all the possible x and y with respect to their probability densities. So it equals to, if x, y are both discrete, okay? So this is summation over x. So you multiply the px, okay? And then you multiply px given x, y equals to 1, plus y equals to negative 1. X equal to x, okay? And multiply by the, so here y can only be 2 values, right? And then we multiply the loss function. So when y equals to 1 and plus loss, if we're predicting x equal to negative 1. Okay, actually this summation is over all the x values, so there is no y involved. And based on the, we can rewrite this equation as, we can factor the y equals to 1 out. So we can rewrite this as equals to, by the Bayes theorem. So in the cancer example, we already derived. So y given x equals to this x given y, you flip the conditional probability and divide by the probability x. So anyway, so to summarize, we can simplify this summation x given y. Before we have y given x, now we flip it, right? We have the x given y, okay, plus you flip the probability x given y equals to negative 1. Okay, so this is called expected loss. Expected loss. Maybe I need more space here before I give you more details about the Bayesian classifier. Okay, in last video we talked about the decision rule and the risk function. Risk function is the expected value of the loss function of the over the different decision rules. And actually the Bayesian classifier. So now we can formally introduce what is called a Bayesian decision rule or Bayesian classifier. The Bayesian decision rule or the Bayesian classifier is Bayesian classifier. Is a decision rule R star such that it minimizes the risk, function. Okay, so that's the definition of the Bayesian classifier. And in the next, I will give you one example. But assume the cost function L that with correct classifiers. So which means if we can predict a cancer patient with a cancer, and we diagnose the patient without cancer with no cancer. So for these two cases, we assume there is no loss, or without any loss, then this Bayesian classifier can be written as, okay, if so what's this decision rule? Decision rule will equals to if this loss false negative, loss for the false negative, multiply the posterior probability y equals to 1 given x is greater than loss for the false positive, which means the original is negative. There's no cancer, but you classify it as a cancer patient, so it's called false positive, and you multiply this posterior probability. If this is greater, if the loss on the false negative is greater than the loss for the false positive, then we classify it as a positive case. Otherwise, we classify it as negative. So intuitively, that's easy to understand, right? But actually, its proof is straightforward from the definition of this risk function. Actually, if we can think here is Rx, okay, maybe there is a very simple proof. If we predict Rx equal to 1 or negative 1, okay, if we predict 1 equals to 1, there's 0, right? So for only non-zero part, we have only two cases. The true value is 1, but we predict negative 1. True value is negative 1, we predict as 1. Okay, and therefore, this risk function will be minimized. Okay, if we so this function will minimize the risk, will minimize this risk. And furthermore, if this loss is a symmetric loss function, okay, then in other words, L false negative equals to the loss for the false positive. If that's the case, Bayesian classifier will just pick the one with the higher posterior probability. Okay, the Bayesian classifier will just picking the class with the biggest posterior probability. So Bayesian classifier will pick the class with the biggest posterior probability. Biggest posterior probability. Okay, so here I give you one example. So let's go back to check the example at the beginning of the class. In the cancer diagnostic problem. So the decision rule, the Bayesian classifier for the, so let's say in the cancer diagnosis example. So the Bayesian classifier will diagnose mapping the features of farmer equals to so here we assume the asymmetric loss, right? So we can calculate false negative, we give loss 5, if you recall. So 5 times false negative, we give 36%. Okay, false negative, we have the loss 5 multiplied 36%. Okay, and the false positive, we give loss 1. We multiply by the posterior probability. Given the farmer, what's probability is negative, it's 64%. So it's and this multiplication is 1.8, and on the right hand side is 0.46, will be greater than. So therefore we predict it's safer to predict. Although the posterior probability is smaller, but it's still safer to predict the farmer has cancer. Okay. Similarly, we can also calculate the decision rule for the minor. Will also given predict as a cancer. Okay, and the other we predict as no cancer. Okay. So this is called the Bayesian base risk and the Bayesian decision rule. And we can also give the risk, calculate the risk. Remember, the risk is just the expected value, base risk or optimum risk. We can also calculate this. By the definition, it's capital R, small r star. Is equals to the probability with population who has cancer is 0.1%, 10%, right? And multiply how many cases we predict as a cancer. Okay, or we predict it as has no cancer, with no cancer. So 5 multiply the loss multiply given the cancer patient among the other jobs, which is 30%. Which is 30%. If you go back to check the original data table here, yes, a 30%. So 0.3. And among the patients without cancer, so we have 90% of the people does not have the cancer, and multiply the loss for the cases we predict as cancer. So in this case, we have 2 cases. One, we predict farmers and miners for the with cancer. So, and then we multiply 1 So loss is 1, right? So false. And with 0.01, 1% plus 1 multiplied 0.1%, 10%. So this is the overall risk. And this gives value equals to 0.249. So this is the optimum base risk if you assign the loss function. Is no other decision rules will give lower risk than this one. So in last video we talk about we give you the example derive the base risk for the cancer problem, and we show that this will be the base. This is the decision rule will give you the lowest risk. For example, if you give another set of the classifier, for example, you classify the farmer with no cancer, the miner with cancer, and other job with no cancer, and you can calculate again by following. I will leave this as a practice for you, and you can calculate the risk. This risk will be higher than 0.249. Okay. And in this video, I will talk about the try to talk about the discriminative analysis based on this Bayesian decision rules. But we're gonna use for the continuous features, not like a discrete features. So for this case, we need some preliminaries for the continuous distributions. Continuous distribution. So if a random variable x has a continuous probability density function, probability density fx. Okay. Suppose x here, for example, x could represent the height of a person, right? As the example I given you in the beginning of the class, or x could be the number of the calories. So height, calories in this case are continuous variable, which means x can have infinite many values, but with decimal numbers. Okay. And for example, we want to use based on the number of the calories intake per day to predict if a person has a cancer or not cancer. So now for this case, what would be the Bayesian classifier? So this classifier, we call it discriminative analysis. Okay. But how do we find out the probabilities of the continuous random variable? Okay. So usually it can be described by the density curve, and the probability of the continuous random variable x between two values x1, x2. This can be solved by using the integrations of the function fx from the value x1 to value x2. Okay, and we can also further to this is the area. This represents the area between these two values under the density curves. This area represents we're gonna use this area represent the probability. So that's for the continuous random variable, and of course, if you do the integration from the positive or negative infinities, we get the total area here. So this gives us the probability should give probability equals to 1. So if you have a well-defined density function, the integration should give you value 1. Okay, and further we can define the expected value of a continuous random variable. For example, if g is a function of the random variable x, then the expected value of the gx can be written as the integration of the gx multiply fx and do the integration. You can think this is a weighted. You can think this is a weighted sum, because integration is just a summation, right? And the special case is if gx is the identity matrix, we can have this expected value of the random variable x can be written as this integration. Okay. Also, the variance is also the expected value of a function of random variable. We denote sigma square usually. It's given equals to the expected value x minus mu square. Okay, this is our gx, and mu is the expected value of the x. Okay, and this can be written as solved by using integration of x minus mu square weighted by the density fx. Okay, so that's some preliminary about the continuous random variable. So now, let's say based on these continuous features, how do we define our classifier, Bayesian classifiers? Okay, for example, based on the number of the calories intake each day, suppose based on our data, we have among the cancer patients, we have this density curve. Okay, and we have another density. Maybe I should use another color. And based on our data, suppose we have two classes, and among the cancer patient, without cancer, no cancer patient, we have one distribution, and with a cancer patient, we have another distribution. As we can see here, suppose these two density, we assume a 0-1 loss. Okay, in other words, correct classification we give loss 0, and wrong classification we give loss 1, and we can solve this. We can say this is one-dimensional distribution where they intersect. Suppose the calories intersect is intersect at x equal to 800. Okay. Now suppose the prior information that we have the so let's derive the Bayesian classifier for this case. Okay, suppose we have the 0-1 loss, and further we assume the prior information. Let's say there are 33%, 1/3 of the population has cancer. And 2/3 of the population does not have cancer. Say this is the prior information. Okay. And based on 0-1 loss, because symmetric loss, we can calculate the risk function. And remember that based on our previous definition of the Bayesian classifier, if we have symmetric loss, our classifier will classify the case with higher posterior probabilities. So first, we need to calculate the posterior distributions. Actually, this is the ratio of this y given -1. Okay, you multiply this 2/3 probability, and you normalize it, you get these posterior probabilities. Okay, so actually this posterior where the posterior density intersect is called the Bayesian optimum decision rule. Bayes optimum decision boundary. In this case, we have recall this is the symmetric, we have 0, 1 loss, right? So we only need to compare the posterior probabilities. This posterior probability equals to the data likelihood, this is also called likelihood, multiply the prior densities and prior distribution, 2/3. So you give the, okay, so below this decision boundary, so this is one dimension boundary, right? We classify it as a no cancer, okay? And above this decision boundary, because this higher the probability, the cancer group has higher posterior probabilities, so we predict with cancers, okay? So this is called a Bayesian optimum decision boundary. And actually, we can also derive the risk function. Risk function. Okay, the risk function can be written as the expected value of the decision loss of decision rules expected values. Okay, recall the formula is given here. But here we use the summation, but now we are using x as the continuous variable, which you just use the integration. So it's the probability y equals to 1 multiply the before we have summation, but now we have integration, Lx1 times this is our expected value, right? Of the function of the gx weighted by the conditional density of the cancer group density calorie densities, okay? And for the negative, for no cancer group, okay, we predict -1, right? The true value is -1, and we multiply the conditional probability x given y equal to -1. Okay, so this is how we find the risk functions. And actually, if you combine these two terms together, because we have the 0, 1 loss, right? 0, 1 loss. For the correct prediction, we give loss 0, and wrong prediction we give loss 1. And so both loss we give the 1, right? We give 1 value. So actually the Bayesian risk is given, the optimal risk is we can solve analytically is integration of the minimum between two density values. Multiply conditional probability density x given y equals to y. times probability y equals to negative y equals to y times dx. Okay. Actually, what's this means? Okay. Actually, it means the risk function is just the integration. Let me redraw this part for you. Suppose now we have the two posterior densities, and the decision rule is, let's draw where the intersect is. Yeah, this is the base optimum decision boundary. And below this decision boundary, we predict no cancer, right? No cancer means density we predict with cancer will be with no the true value is no cancer, but we predict with cancer case. So this is the integration. So actually the risk is just the area in the shaded area I labeled here. So this is the optimum risk for the Bayesian rule. Okay, so this is called the Bayesian classifier with this is actually you can think this is the simplest discriminant analysis. So now for the higher dimension, I'll show you another plot. Okay, for the higher dimension, among the cancer and the no cancer group, we can fit two distributions. For example, here we fit two normal distributions, and the base optimum decision boundary is where these two density surface intersect each other. Okay, this is the posterior distribution, and this is the decision boundary. So this is the Bayesian classifier. This is also called the least discriminant analysis. So this is for higher dimension. For dimension 2, we can give a plot. But for the dimension, if we have feature more than 2, we cannot make the plot. Notice that the accuracy of the probabilities is most important near the decision boundaries. And far away from decision boundary, a bit error in the probability won't change the classification at all. So this is the Bayesian classifier we constructed is kind of robust to the outliers. And you can also have the multi-class classifier easily. If you have not only two groups like cancer, no cancer, but we have like you classify the handwritten digits, right? You have the 10 classes. You can also apply the similar procedures. The approach is very convenient for you can easily to generate your classifier from the bivariate label to the multi-binary classification to multi-class classifier. Okay, so far we learned several ways to build the classifiers. Maybe it's good time to give a summarize. So first case, the least least discriminant analysis. Discriminative analysis. Okay, which is built based on the decision theory, and we assume samples are from different distributions. Different distributions. Okay, for example, for the cancer group, we have the one distribution, and for no cancer people group, we have another population, calorie distributions. Okay, and for each class, we just fit a distribution. We can using the normal distribution, multivariate normal distribution. Fit some distributions. For example, for each cancer group, we fit the one normal distribution. For another no cancer group, we fit another normal distribution. Okay, and then we can also estimate the prior probabilities. We can get a rough estimate how much population has cancer, how much population doesn't have cancer. We can have an estimate. And then we can calculate this posterior distribution. Okay. Once you calculate posterior distribution, you can pick a loss function. And then you can use the formula I introduced in today's class. We can build a Bayesian classifier. Okay, so the second way to build the classifier is based on the discriminative models. We can directly solving the conditional probabilities of x given y given x. We assume it follows some distributions. For example, based on the logistic regression, we can directly estimate the distribution of the label given the predictors. So it's called logistic regression. And the third method is sort of the deterministic way. We ignore the probabilities. We can find the decision boundary directly, for example, using the support vector machine. Okay. So the advantage of the first two methods, least discriminant analysis I introduced today, or the logistic regression I introduced in future classes, is that it involves a probability distribution, which can work better for if you have data that is not linear separable, or you don't have the clear cutting boundaries between the classes. But there is you need it provides a probability for your guess. Okay, and there is also disadvantage. But the support vector machine cannot just give you the decision boundary. It didn't give you the probability of your guess is correct or wrong, right? And in a lot of applications, people want to know the probability of your prediction is correct or wrong. Also, there is also disadvantage of the first discriminative analysis. You need to estimate these posterior distributions. For example, to derive the posterior distribution, you need to fit the multivariate distributions. But estimations problem for the higher dimension date features, for example, you have the 20 features, you fit a normal distribution, even if assume it follows normal distribution, it's quite a challenge. Okay, it is a challenge to estimate the distributions for each class. Okay, I think that's all I want to talk about today. Thank you.